Hey everyone, Mr. Hauk here. So this is my third or fourth attempt at recording this video. I ended up finding out that every time I tried to leave this GoodNotes app and go over to Desmos to show things in Desmos, it would stop the screen recording. So I'm going to stay in GoodNotes and I'm just going to trust that you guys have Desmos pulled up somewhere and that you can plug into Desmos and check these things, okay? So I'm not going to be going over to Desmos. I'm going to stay right here in GoodNotes and talk about the review, go through this performance final review, because if I try to go to Desmos, it's going to end the recording. All right, so for problem number one, we're on the AP Precal Fall Performance Final Review. Problem number one, function f is given to us in a table. So we don't know function f, but we have the table values. Function g is this rational function right here. In part A, part 1, we have a new function h, and h is g of f of x. So h is a composition of functions where we're taking function f, we're plugging it into function g. This is what we've been doing here at the beginning of Unit 5. All right? We want to find the value of h of 2. So h of 2, well again, h has been defined as g of f of x. So we're going to replace x with 2. So h of 2 is g of f of 2. To calculate this, we start with the inside. We need to calculate f of 2. F of 2 is 14. We get that from the table values. Now that we know f of 2 is 14, now we can calculate g of 14. Plug 14 into the function for g, and you should get 2,258.412. All right, part 2 for part A. Find the value of f inverse of 7 or indicate that it is not defined. When I'm doing, inverse value problems, I like to look at the inverse and the original function. Remember that a function is inverse, the x and y values, the inputs and outputs, they get swapped. So this is telling us that 7 is the x value for f inverse. If 7 is the x value for f inverse, it's the y value for the original f. Up on the table, we can see that f has a y value of 7 when its x value is 1. So if the x value of f is 1, then the y value of f inverse is 1. And that answers our problem for us. F inverse when x is 7 is equal to 1. All right, part B, part I. Find all values of x as decimal approximations for which g of x equals 3 or indicate there are no such values. So we're trying to figure out when does the function g equals 3. And remember that the function g is the rational function. So we're trying to figure out when does that rational function equal 3. Since you're going to have Desmos available to you on the performance final, here's how I recommend solving this. I would take your function g, plug this into Desmos, and in the next equation line, type y equals 3. So put your function g in one equation line, put y equals 3 in the next equation line. This is going to graph your function g, and then it's going to put a horizontal line going through 3. And if you find where that horizontal line intersects your function g, that's going to tell you where your function g is equal to 3. And these are the two x values that it happens at. You can check those in Desmos. All right, part 2 for part B. Determine the end behavior of g as x increases without bound. Express your answer using the mathematical notation of a limit. So limit notation for end behavior looks like this. Remember that this means right side end behavior. If it was x approaches negative infinity, it'd be left side end behavior. But this tells us x increases without bound. That means x is going towards positive infinity. So this represents the right side end behavior of the function g. And if you did what I said to do in the previous part, you already have function g graphed in Desmos. So look at the function you already have in Desmos. You're going to notice that as you go to the right on that function, your function values are going up towards infinity. All right, part C, part 1. Use the table of values of f. Determine if f is best modeled by a linear, quadratic, exponential, or logarithmic function. Well, if you look at your table values for f, the outputs are the inputs are changing by the same amount, the outputs have a common ratio of 2. So if you have equal intervals of x and you have a common ratio for the y values, that means it's an exponential function. And part 2 for part C is the reasoning. There is a common ratio of 2 over equal intervals of x. So that's the first page of the performance final review. I really think the first page is pretty simple overall. The second page definitely gets a little bit more mathematically involved. So let's talk about the second page of the performance final review. So, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 110 flies, and after 4 days, there are 315 flies. The population of fruit flies can be modeled by the function right here. P of t equals ae to the bt power. P is representing population of flies, A is the initial amount, T is the time, specifically days, and B is the growth rate. E is the natural base. We know E to be 2.718 ... Okay? So, one of the challenges is this equation has 2 different unknowns, A and B. We need to find both of them. That's what part A is trying to get us to do, is to find values for A and B. The way that we're going to do that is we're going to take this information that I have highlighted, we're going to make 2 equations out of that. So when T is 2, P is 110. If you plug those in, so plug in 110 for P, plug in 2 for T. We get this right here. 110 equals AE to the 2B power. Now, when T is 4 and P equals 315, we get 315 equals AE to the 4B power. The idea is both of these equations have 2 unknowns. That's why we needed 2 equations. What we're going to do is we're going to take equation 1, we're going to rearrange it so that we get A by itself. Once we get A by itself, we're going to replace the A in the second equation with what we rearranged for equation 1. Then we're going to try to solve for B, and once we solve for B, we can plug B back in, and that's going to allow us to solve for A. Okay, so let me show you the steps to do that. All right, so first, take equation 1, which is right here. Go ahead and get A by itself by dividing both sides by e to the 2b power. All right, so this is what we have now. Once you divide both sides by e to the 2b power, we get this. Take this for A and plug it into equation 2. So where you see the A right here, you're going to plug in 110 over e to the 2b power. So that's what I have right here. Now, notice that here, this e to the 4b power, this is in the top. This e to the 2b power is in the bottom. There's an exponent rule where if you have the same base with different exponents and you're dividing, you can simply subtract the exponents. So 4b minus 2b just gives us 2b. Okay? Now the goal is to try to get this b by itself. So first we're going to divide both sides by 110. That gets us right here. Then here's the tricky part. In order to get into this exponent to get b by itself, we need to get rid of our base e. To get rid of e, we use its inverse natural log, which we learned about in the previous set of notes. So I need to take the natural log to get rid of e, but because it's an equation, what I do to the right side, I also have to do to the left side. So take the natural log of both sides. Natural log and e cancel each other. Now all we have left on the right side is 2b. And to get b by itself, divide both sides by 2. Plug this into Desmos or your TI-84. You get that b equals 0.526. All right. Now that we know b, we can go back to what we had for a. When we got a by itself, we can plug in the value for b. That's going to help us solve for a. So that's what I did. I took what we had for a. I plugged in what we got for b right here. Notice, by the way, I'm not using the decimal. We had to round that decimal. So we don't want to plug a rounded answer into something else because then it's going to be a little bit inaccurate. So notice that I'm plugging this in for B. Okay, throw this whole thing into Desmos or your graphing calculator and you get that A equals 38.413. Now let's say that you had plugged in 0.526 instead of this. I think you would have gotten 38.416 or something along those lines. So a little bit less accurate. This is your most accurate 3 decimal approximation for A. All right, part B, part 1. Use the given data to find the average rate of change in the number of fruit flies in fruit flies per day from t equals 2 to t equals 4 days. Express your answer as a decimal approximation. Show the computations that lead to your answer. So we have a formula for average rate of change. It's f of b minus f of a over b minus a. It's essentially the slope formula. So it's kind of like calculating the slope from day 2 to day 4. So p of 4 minus p of 2 over 4 minus 2. Well, p of 4 is 315. That's the population on the 4th day. Minus p of 2 is 110. That's the population on the 2nd day. Those values were given to us. Divided by 4 minus 2. This gives us 102.5 fruit flies per day. Part 2 for part B here, interpret the meaning and context of that average rate of change. So this means, because it was an average rate of change, on average, the population of fruit flies is increasing by 102.5 flies per day from day 2 to day 4. All right, part 3. Consider the average rates of change of P from t equals k to t equals 2 days, where k is between 0 and 2. Are these average rates of change less than or greater than the average rate of change from t equals 2 to t equals 4 days? So we're looking at the graph. Again, I can't go over to Desmos because it's going to end the recording. So I did a little sketch here. We're looking at the graph and determining, are the average rates of change from 0 to 2 less than or greater than the average rates of change from like 2 to 4? Well, because it's a concave up exponential growth function, the slopes are getting steeper the farther right we go. So your average rates of change from 0 to 2 are going to be less than the average rates of change from 2 to 4. And then finally, part C. Through observations, this function model P was shown as an appropriate model when the population of fruit flies is less than 100 times the initial amount of fruit flies present. Based on this info, on what day does model P fail to be an appropriate model? So what it's saying is, this equation, and I went ahead and plugged in A and B that we found previously, so this is the equation. This equation is a good model until the population is 100 times the initial population. That initial population was 38.413. That was the A value. So once the population is 100 times the initial, then it's a bad model. So we're trying to find out on what day is the model equal to 100 times the initial. Well, 100 times the initial, which is 100 times this, is 3,841.3. We want to find the time, the day, when this equation is equal to 3,841.3. So plug this into Desmos, plug y equals 3,841.3 into the next equation. You're going to have to zoom out a lot because this is 3,841, but zoom out a lot and find where that horizontal line intersects this. You'll find that that happens at 8.755, so the model fails to be appropriate on day 8. All right, y'all. Hopefully this helps explain some of these problems on the performance final review. I will catch y'all later.